Okay, so we're going to start. There's two types of line integrals. There's line integrals for a scalar function. So this is like if we have a surface, if we have some function um, f of x and y, right? And this just gives us some surface like this. Okay, we can do a line integral with this, or we can do a line integral for a vector function. And we'll talk about those in a second. Okay, so if you recall before, I had talked about if we had like a surface and we wanted to do the derivative along this curve, right? So we have some function of x and y, and I have a curve r of t, right? It's some parameterized curve. I could do the derivative along this curve, right, by doing this. I would do the gradient of f at r of t dot r prime of t. And this was how I could do the derivative along this line. Okay, so now we're going to do the opposite of that. Now we're going to integrate along this line. Okay, so like you see in this picture, the integral along this curve is going to be the area under this curve. Okay, so let's look at this. How do we compute the area, right? We chop this up into rectangles, and then we figure out the area of the rectangle. Okay, so for this rectangle right here, the height is going to be the value of the function at some point. And then what is the width of this triangle? It's the length of a small segment. And then we're going to add all of those rectangles up together. Okay, so when we do the limit, as these rectangles get small, this becomes integral of f of xy ds. So does anybody remember back, like way back to like February, when what ds was? Does anybody remember? Or how about this ds and dt? Speed. Okay. Yeah, that was true. So we also said that that was equal to r prime of t. Okay, that's fine. But what is r prime of t? That is square root of x prime squared plus y prime squared. I'm sorry, not r prime, because this is a scalar. It should be the magnitude of r prime. Okay, so if we have this integral and I want to integrate f of xy ds, I can basically think of this as multiply and divide by dt. So this is f of x y ds dt times dt. Now I want to restrict this to only integrating over a certain curve, right? That's the only way this t makes sense. So I'm going to put c here for whatever curve I'm integrating over. This is going to be r of t. So to finally put it all together, this integral over whatever curve I'm interested in of xy ds, this is going to be equal to the integral from t0 to t1, or whatever t's we're interested in, f of r of t times r prime of t dt. Okay, so this whole bit right here, right, this basically corresponds to how long this segment is, and this part right here is how tall the segment is. Okay, so why would we want... Okay, it's gonna get loud, might get loud here for a second. So why would we want to do an integral like this? What would that represent? Um, so one plate application where you would find this is if anybody's done like thermodynamics or messed with or learned about like Carnot cycles and Carnot engines. Um, they have a so you have the let's see, imagine you have some sort of pump like a piston or something, right? And you can push this down, and if you push it down, the volume goes down and the pressure goes up. Okay, so you have this kind of diagram of what happens, what the volume is, what the pressure is, um, and how that affects the temperature. So here, basically, if you were to integrate um, the temperature along this curve, it would tell you how much heat is being generated or put in or taken out from this system. So that's exactly what this would correspond to. You're doing an integral along this line, and then you could figure out the total work done by an engine by pumping this in and pumping it out by doing the integral along the total curve. So yeah, basically when we want to integrate something along a line, along a specific line, this is how we're going to do it. Okay, so let's do an example. Evaluate this integral where c is the upper half of the unit circle x squared plus y squared equals 1. So we have this.
Mic off. Mic on.
So I need a way to parameterize this curve. Okay, well, so I can always do this as r of t equals cosine t. Let's put it like this. And then sine t, like this. So to go from here to here, that means that t starts at 0 and goes all the way up to pi. Okay, so for these, it's really important to note on your diagram, or when you're parameterizing your curve, where does t start and where does it end? Now, it really does not matter how I parameterize this curve. Okay, as long as it describes the same curve, how I parameterize it does not matter, right? Because the area is going to be the same no matter how I describe it, as long as it's the same curve. Okay, so here's my r, and I want to integrate integral over c 2 plus x squared y ds. So we know that this is going to be the integral from 0 to pi of 2 plus, that's going to be cosine squared t times sine t multiplied by the norm of r prime. What is r prime? That's going to be derivative cosine is negative sine, derivative sine is cosine. Okay, so the norm of that is sine squared plus cosine squared. That's just going to be 1. So we don't need to actually change anything here. We can just multiply by 1 dt. Okay, so real quick, again, to recap what I did, I put in my bounds for t. I changed these to match the coordinates, right? This is x of t, this is y of t.
Mic off. Mic on.
and then I multiplied by ds, right, which is r prime of t, or the norm of that. Okay, um, actually, hold on. Let me go back and change one statement I made. I said it doesn't matter how you parameterize the curve, and that's true as long as you're going in the same direction. If I was, let's see, why did you use cosine and sine for x and y? So because I'm trying to describe the first half of the circle, let me draw this a little bit bigger. So here, this is my curve, right? So if I'm going along this curve, what's the x coordinate here, right? That's going to be the cosine, but I can just describe this as cosine of t of some angle, and sorry, this is cosine, and then the height is going to be the sine. So it's just because I'm describing a circle, right? It'll be different for different curves. Um, so I was saying that it doesn't matter how you parameterize it, as long as I'm going in the same direction, right? As long as when t gets bigger, I'm going this direction, right? Because if I was to flip these and go from here to here, this integral is going to switch to being negative. Um, it's just going to be the negative of what I'm supposed to have. So as long as it's going in the same direction, we get the same integral. So I integrate this real quick, and I get 2t set u equals cosine t du equals negative sine t dt. So that's going to be minus cosine cubed over 3 from 0 to pi. So that's 2 pi minus cosine of pi is negative 1. And then we do minus 0 minus cosine of t of 0 is 1/3. So we have 2 pi, that's going to be plus plus, that's positive. 2 pi plus 1/3. Okay, did that answer your question on why I used sine and cosine? Wouldn't it be 2/3? Yes. I think I said that, but yeah. I think I said 2/3 and wrote 1/3. Okay, so if this is a scalar function, so notice, right, it's just a scalar function, this is the same process. Sometimes the curves can be a bit strange. Okay, so here's an example. Okay, evaluate the integral over this curve where c consists of the arc of the parabola x squared from 0 to 1, so that's this. This is 1, followed by the vertical segment from 1 to 1, 2. So then after we get here, that's the point 1, 1, it goes straight up. That's not, I'm not drawing straight, hold on. Okay, so we have a parabola up here to the point 1, 1, and then it just goes straight up to here. So this is 1, and this is 2. Okay, so here I have two segments. So what I'm going to do is just like I would do with a regular integral, I'm going to break it up into two segments. So I'm going to have the integral, I'll call this part C1 and this is C2. I'll integrate over C1 and then I'll integrate over C2. Um, right, so here the ds is going to be different because they're different curves. So C1, right, that's this parabola part. How do I parameterize this? Any guesses? How should I parameterize this part? Looking for a guess. Somebody. No? Okay, well, there's always a very easy to parameterize any curve that you know the equation for. I said x equal x of t is t, and y of t is just t squared. So with this, I have, so r of t is going to be t squared. R prime of t is 1 to t, and the norm of r prime is square root 1 plus 2t. Sorry, that's going to be 4t squared. Okay, so I want to integrate. Oh, and where does t start and end? T goes from 0 to 1. Important to note. Okay, so here t goes from 0 to 1, and then we integrate our function, which was 2x, so I'm going to put 2t, times the norm of r prime, which is 1 plus 4t squared dt.
Mic off. Mic on.
Okay, so I integrate this. Let's see, I'm going to set u equals to 1 plus 4t squared. So du is equal to 8t dt. So it looks like I should multiply and divide by 4. So now I can write this as the integral, or 1/4 integral from of square root u du. And when t is 0, this is 1. When t is 1, this is 5. Okay, so that's going to be 1/4, 2/3, u to the 3/2, 1 to 5, which is 1/6 times 5 to the 3/2 minus 1. Okay, so that was this first bit. That's the integral, the line integral, under this C1. Now I need to do the second half, C2. So how can I parameterize this curve? Well, this just goes straight up. So C2. So if x is constant, so x is just going to be equal to 1. X is the same the whole time. So I have x, and my thing just froze up. What happened? One second. My notepad just froze up. There we go. Okay, so we have x of t is just going to be fixed at 1. This is a weird angle. What is going on? Okay, so x of t is equal to 1, and y of t, we can just put that as equal to t, where t starts at 1 and goes to 2. Okay, not sure what's going on with my tablet right now, but so here t, it starts at 1, right? So my y starts at 1 and it goes up to 2. So that's what I'm doing. I'm just saying t starts at 1 and goes up to 2. Okay, so I can integrate this. So I integrate over c2. So that goes from t equals 1 to 2 of 2x, which is 1. And then, so I have r of t, which is 1 and t. So r prime of t is square root, nope, is going to be 0, 1. So the norm of r prime is just going to be 1. So here I multiply by 1 dt, and we get 2t from 1 to 2, which is 4 minus 2, which is 2. Okay, so to put it all together, I need to do my total integral. This is going to be 1/6 5 to the 3 halves minus 1 plus 2. Okay, so if I have multiple segments, I need to parameterize each of them individually and do the process for each segment. So the hardest part about this is figuring, and actually about this whole section on line integrals, is figuring out how to parameterize the curve. The rest of it is just regular integration, and just remember to put that ds, we're integrating d with respect to ds, so we have to do r prime dt, norm of r prime dt. Okay, also you want to make sure that the parameterization goes in a consistent direction, right? So here I went from 0 to 1, and then I went from 1 to 2. I would have gotten a strange answer if I would have gone from here to here and then jumped from here to here. Right? That wouldn't have been correct. I would have gotten a negative here. Okay, any questions on those? No, we're good? Okay, I'm going to try restarting this program real quick. Let me save that real quick. I'm going to try restarting this real quick, see if that makes my problems that I'm having go away. So 1 second. Okay. And let's try this again. That's still not doing it. Okay, whatever. Okay, so the next section is on vector fields. Okay, so in all of these functions we've seen before, we have a function. We put in an x and a y value, and it gives us a scalar value out at the end, right? So this is what we call a scalar function. Okay, so now we're going to look at a vector function. So this is going to be something where it's a function where we put in an x and a y, and it spits out a vector. I'll call this spits out a vector. I'll call it p and q, for lack of a better term. Okay, so we've seen one example of a vector function, and that would be the gradient of a let's call this capital F. Okay, so we've seen one example of a vector function, and that is the gradient of a scalar function, right? Because here, if I plug in any x and y value, the vector I get out is this and this. Okay, so here, the vector that I get depends on the x and y coordinates that I'm putting in. Okay, so let's look at a couple examples of where those are used. So for example, if you want to measure the wind speed, right, you would represent this as a vector function, right? It depends on where you look, the wind is going to be blowing at a different magnitude and in a different direction. Or if you're looking at air moving over like the wing of an airplane, right? This is the side view of an airplane wing, right? The You can have vectors that represent the direction and magnitude of that flow. Another example would be like a electric force field. So here, this describes the force due to some electric charge, um, due to like some electric charge or something at, or actually, I guess this would be magnetic charge or magnetic field, but whatever. It describes the force due to magnetism at each point, right? So at this point right here, it feels a force going in this direction. Okay, and each point it kind of shows you the direction that the force is being felt. Which way is it going to be pulled? And same thing here, right? So here we're just kind of following these along. So that's the point, is that at each point in the xy space, we have a vector. Okay, so this concept of force is going to be the one that's most useful for us, where we have a lot of force acting along a line. Okay, so say I have a curve and I have some vector field. It does whatever. Don't really care. But now what I want to know is if I add up the component of all of these vectors along this curve in the direction of this curve, what is the net result? So why would we be interested in this? Let me give you a more physical example. So in physics, you learn about work. Does anybody remember what the definition of work is or how you calculate it? Anybody take physics 1? Nobody? I thought everyone was like an engineer. Okay, fine. So work is equal to force times distance. Okay, so I do a force and I look at how much did I push. Or if I'm pushing an object, I look at the amount of force that I applied and how far did I push it, and that's going to be the amount of work that was done. So, what if I was to be pushing a box along kind of a zigzag path like this? Right, so I'm kind of pushing, um, you know, I'm pushing at a along this curve, but maybe, or so it's moving along this curve. So I have a box and it's kind of moving in this direction. But maybe I'm always pushing it in that direction. So I'm pushing it in this direction, but it's still, or maybe I'm pushing it, it needs a little bit of an upward component. Maybe I'm not actually pushing it along that line. Maybe I'm pushing it, kind of maybe slightly at a different angle or something. Okay, so this angle that I'm pushing it, the vector that I'm pushing it at, that's f. And then if it moves a small bit in this direction, I can call that dr. So the amount of work done to move this, when this box moves up just a little bit from this force, is going to be f dot dr. Okay, so if so that's going to be a small amount of work done. Is like this. So if I was to add all of the amount of work up along this whole line, right, that's going to be the integral of all of that work from A to B, which is integral of f dot dr. Okay, and this is the line integral for vector functions. Okay, so it's kind of adding up the components of a vector field along a given path. That's still not working. So let me find an example real quick. Yeah, let me copy an example real quick. Okay. So here, I want to evaluate the line integral of this vector function along this curve. Okay. So how do I do this? If I want integral of over some curve of f dot dr. So the easy way to think about dr is, again, if I intrinsically think about multiply and divide by dt, right? This is dr dt times dt.
Mic off. Mic on.
Okay, so I'm going to do the same thing I did before, except I just have to remember that dr dt now is a vector, and I'm going to do the dot product with f. Okay, so before, right, I had the magnitude of dr dt. Now I have a dot product. So r prime of t is equal to 44 t cubed and then 3t squared. And we know that t goes from 0 to 1. So this is going to be the integral from 0 to 1. It gives me the parameterization for the curve. And I need f dot, so that's xy, not xy, I'm sorry, I need to write that in terms of the parameterization. That's going to be x, which is 11 t to the fourth, times y, which is t cubed. Sorry, that's my x component. And then I have 3y squared, so it's going to be 3 times t cubed squared dot r prime 44 t cubed 3t squared, integrate with respect to t. Okay, so I do the dot product and I get what? I get, let's see, that's 440 plus 484. So that's t to the 7, it's going to be t to the 10. Right, t to the 4th times t to the 3 is t to the 7 times t cubed, which is t to the 10. So that's this plus, that's going to be 9. That's t to the 6th times t to the 8th dt. So I integrate and I get 484 t to the 11 over 11. I know that cancels out to 44 plus t to the 9 over 9, 0 to 1. That's equal to 44 plus 1. It's 45. Okay, so it's a very similar process, except again, now I have a dot product instead of, multiplying. And this represents something quite a bit different. Okay, this represents adding up the components of a vector field along a line, whereas before we were interpreting it as the area under a given curve for a given surface. So let's find another one.
Mic off. Mic on.
Okay, so very similar, except now we have 3 components. That's no big deal because everything we did, generalizes very easily to 3D. So again, let's calculate r prime first. That's going to be 1. Derivative sign is cosine. Derivative cosine is negative sine. Okay, and I don't need the norm of that because I'm doing a dot product. So I want the integral, and it tells me t goes from 0, well, let's just put c f dot dr. So that's going to be the integral from 0 to t. I'll put f of r of t, sorry, not 0 to t, 0 to pi dot r prime dt. Okay, so we integrate, or let's actually write this out. So we integrate from 0 to pi. So z is going to be cosine of t times 1, right? So I'm doing f of the, let's see, so let me just write this out. So that's the x component. This is going to be sine. That's the y component, and the z component is negative t. Okay, and then dot r prime, which is 1 cosine t minus sine t dt. So we multiply and we get integral from 0 to pi cosine t plus sine t cosine t plus t sine t dt. Okay, so we can integrate each of these individually. Integral of cosine is sine. Let's see, so that's just going to be sine of t from 0 to pi, which is 0. Should that be 0? Yes, that's 0. Okay, and then this, I can rewrite this as 1/2 sine of 2t. So integral of sine is negative cosine. From 0 to pi. And then here we need to use integration by parts for this last one. So I'm going to differentiate t and get 1. And I have sine. Integrate that and get negative cosine. So I'm doing integration by parts. So here this becomes minus t cosine t from 0 to pi, minus the integral from 0 to pi of cosine of t, which we already saw was 0. Okay, so I plug everything in and I get cosine of 2 pi, that's minus 1 over 4. Cosine of 2 pi is 1, and cosine of, okay, so that's times 1, minus cosine of 0 is also 1, so that's going to be 1/4. Those cancel out. Minus pi, cosine of pi, which is negative 1, minus 0. So all of that cancels out, and we just end up with pi. Just like that. Okay, let me see if I can find one more. Actually, let me go ahead and mention this. If I have some curve and it goes in a complete circle, so this is my curve, right? So it starts here and it ends at the same point. Typically, they write this as an integral with a circle like this, right? They might also indicate the orientation, but this means that you're integrating over a loop. Okay, so if you see this funky symbol, that's all it means. It just means that you're integrating over a loop. And you could have
Mic off. Mic on.
you could have this, or you could have more often something like that. Okay, and again, all that circle indicates is that you're integrating over the entire loop, so that the start and end points are the same. Okay, questions? Any questions? So I hope you can see that these ones, they're a little bit simpler. The hardest part about these is if you have to come up with the parameterization yourself. Sometimes that can be not as straightforward. Hopefully you've had a little bit of practice with that. But the actual integration part is not hard. Okay. For a vector field, you do f.dr, and for a scalar function, at the area under the curve is f times ds, integral f ds. There we go, f ds. And there's all kinds of examples, interesting examples on where this actually gets used, because now that we're getting into vector calculus stuff, the stuff we talked about has a lot more physical applications to physics and mechanics and stuff. So if that interests you, I can give more examples. All right, I'm going to go ahead and stop the recording.